Just somebody tell me you can see and hear me. Right, thank you. Okay, where are we? We are going to go to, yeah. Right. Okay. So we're just gonna not going to spend too much time on this. We won't do the algorithms today. We'll do them the next day. But we'll just sort of introduce the whole concept of what we're going to be looking at and things called page faults. Anybody ever heard of a page fault? Anybody know what a page fault is? Okay, well, the good news is in about 20 minutes, 25 minutes, you will know what a page fault is, okay? Right, running process. When a process needs executed, its corresponding virtual pages are loaded into DRAM. I think we know that at this stage, thank God. Remember, your program is stored in hard disk or SSD. You create an instance called a process, and the chunks of the process required for the process to actually run must be loaded from disk to DRAM. The process address space is virtual, so we need a page table. Not all of the process address space will be fully loaded to DRAM at any given time. Right, okay, so hopefully at this stage you know what I mean. And here's it in words for a very, very simple example. When a system allocates a frame to any page, it translates this logical address into physical address and creates an entry in the page table to be used throughout the execution of the problem. Whoopie-doo. Suppose you have a program of 8K, a process of 8K. So in the brain, logically, virtually, that is viewed as sequential. But your DRAM memory can only accommodate, say, 5K at any given point in time because the rest of it is taken up. All right. When a computer runs out of DRAM, in other words, when the 5K is taken up, the operating system will move idle or unwanted pages of memory, the DRAM memory, to secondary memory to free up RAM for other processes. So, for instance, remember we did process and we talked about suspending and resuming, and we said you can, when you suspend, stuff that's in DRAM process control blocks gets hoofed out into secondary. Here's another example of some of those could be taking up valuable DRAM and they get hoofed out. Okay, and it brings them back when you need it, like resuming. And there's a reminder. Okay, this page moving continues during the whole execution of a program, where the OS keeps removing idle pages from main memory and writes them into secondary and brings them back when required by the program. Now, sometimes it writes them out of secondary, like in the case of suspend resume. Sometimes it doesn't. Sometimes it's just bringing in a new page from hard disk into the DRAM. It doesn't need to write anything out to the hard disk. It's just bringing new ones in. Okay. The more paging one needs, the slower the process. That's why everybody wants more DRAM on a piece of. Okay, so that's just a very, very simple summary of where we are. Hopefully, most people get it. So there's that. I'm not doing it again. I've done it 3 times today. Okay, but basically, we run it. We have 5 pages there. We need to bring in 13, 14. 13, 14 get brought in. 1 and 2 gets hoofed out. Why? We use a FIFO algorithm to get rid of it. More on that later. So a page fault. What's a page fault? It typically happens when a running process tries to access some virtual memory in its address space that is not mapped into physical memory. Well, we have just seen that. We saw 20 try to allocate page 30, try to address page 13. Page 13 wasn't in because it was full up. So a page fault is issued. Remember, we said that's an interrupt. The MMU interrupts the process and says, here, I need you to get rid of something out of DRAM so I can bring in page 13. And lo and behold, in comes 13 and 14, and we move on. So here's a question for you. In the running of this program, right, we needed chunk 1, 2, 3, 20, 21, and then 13 and 14. How many page faults were there? Helen says 5. Anybody else? Come on, be brave. Think about it. Every time I need to bring something from hard disk to DRAM, I'm going to get a page fault, right? Even the first one. First one goes to run. Remember, I can't run from here. So the MMU goes, oh, he started off, he wants to run chunk 1. Chunk 1 is not in, right? At the very start, none of these were in. So 1 had to be brought in. That's a page fault. So now I'll ask you again, how many page faults are there in the running of this program? 7. Well done, Ivan. Okay. Every time you bring in a chunk, there's a page fault. All right. Now, this example, there was no chunk was revisited, right? So it's just 7. In examples we will do next week, we will be revisiting pages. Sometimes they will be in there, sometimes they won't. And if they're in there, you don't need a page fault, all right? Because it's already in there. So remember, this is all about maximizing the use of this DRAM or minimizing the number of page faults. Page faults are bad because they take time, right? Ideally, we would bring all our program into DRAM and leave it there while it ran, so when it revisited chunks, it didn't have to do new page faults. But in reality, that doesn't happen, okay? Especially if you don't have a lot of DRAM. If you've got 2 gig of DRAM, good luck, you've got a lot of page faults. If you've got 4 or 8 or 16 gig, you've got less page faults. Right. We'll keep going. Page faults can occur in other situations. There's 3 types: minor, major, and invalid. Well, major is the one we've just done, okay? Minor versus major. If a page fault handler can satisfy a page without incurring disk I/O, it's treated as minor. What the hell is that? Right, we'll come back to that in a minute. If the page fault has to incur disk I/O to satisfy a page request, it's treated as a major one. Okay, that sounds like what we just had to do, okay? Because we had to incur disk I/O. We had to get our page from hard disk into DRAM. So they were 7 major page faults. So what the hell is a minor page fault? Minor. We need to update the page table, but we don't need to get anything from hard disk, right? So we don't have I/O from a hard disk, which is slow, obviously, compared to DRAM. But we had to update the page table. Why would we have to do that? So the example is below. Mapping shared library code to process B virtual memory after that code has already been loaded into DRAM by process A. Oh, okay. Right. What's that mean? Has anybody ever used a shared library or a DLL? You've all used DLLs, whether you know it or not, right? Every program that runs on Windows uses a DLL, right? A DLL is a dynamic linked library, okay? It's a shared piece of code. So you won't find it, you find one copy of the DLL, agreed, on the hard disk. You don't find it built into every program that needs that DLL. Otherwise, every program would be enormous, right? So what happens is the first person, say we have DLL, pierce.dll. First person that needs pierce.dll, maybe it only needs a few functions out of pierce.dll. When it tries to access them, those few functions out of pierce.dll are brought into the DRAM. Page table is updated, right? Now, if someone else uses pierce.dll, guess what? It doesn't need to bring it in again from the hard disk. It's already in there, right? What it does is it manipulates the page table to say that this other process is also using pierce.dll functions, right? Same ones as the other guy's using. So we don't need to have it in there twice. All right? Because what's the only difference between the two of them? The offset. And that's going to be contained in the virtual address. So therefore we don't need to have the block. We don't need to bring it in twice. It's already in there. Hopefully you can see that. So a minor page fault is basically, I don't need to bring the stuff in again. I just need to update my page table. It basically says that page in that process is mapped to that frame, right? Because it's the same frame as someone else is using. The only difference is the offset, where they are in that block. Hopefully you can see that. That's what a minor page fault is. And we have another example in a minute. It's the same example. That's the major one. Well, I'm not going to do that again. We just did that. Blah, 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 blah. Okay. If it happens, if you're doing a lot of major page faults, right? In other words, if you have very little DRAM left and you're running a lot of stuff, like a lot of programs, you'll trash the CPU. Now, in the old days, that was noisy because there was stuff being dragged in and out from hard disk all the time. And a hard disk is a noisy piece of kit because it's a mechanical device. You don't get any noise these days due to SSD because it's just a memory addressed chip. There's no moving parts, but you still will be overworking your MMU and your program will be going very slow. Okay, that's a major page fault, and major page fault is those ones. Minor, I don't really do examples of minor, bar the description I gave you there. Okay. An invalid page fault is very simple. Your program is acting the maggot, your process is acting the maggot, and it's trying to access someone else's memory. And so the MMU goes, you're not allowed to do that, and it gives you a segmentation violation. And you've all done that as well. And if you haven't, you will. So, which page? When you're trying to figure out which one to get rid of, like this, we decided to get rid of 1 and 2 and bring in 13 and 14 because we used a FIFO algorithm, first in, first out. There are other algorithms. Let's have a look. It's common in paging systems for all page frames to be in use. It's common for your DRAM all to be in use. Therefore, when a page is to be brought in, another page must be moved. That's fine. The objectives of page replacement strategy are to keep in main memory what is most likely to be used in the near future. So we all now have to have crystal balls because we can see what's going to be used in the near future. I don't think any of us can tell what's going to happen in the future, but with programming, we actually have a fair chance of figuring out which pages are going to be used in the near future, and due to a few things called locality, right? And what it means is typically, and we'll talk about it in a second, typically a computer program when it's running, it's doing loops or it's constantly calling the same methods, right? Therefore, if we keep pages in memory that were fairly recently used or pages that are close to the pages that we already have in, the odds are high we're going to use them in the near future. Okay, so just bear with me for a minute and I'll explain it more on another slide, but that's basically what we're saying. If you have used a page in the recent past, you probably jump to a method in that page, then the odds are high due to the way programs work. You might have to call it again, right? So we'll keep that one. Or if we're on a certain page, the odds are high that the way computer programs work and they just flow sequentially, a lot of the time, if it's a big method or a big function, we could need the chunk that's right beside us. So therefore, we'll keep chunks in memory that are close to each other as well. So there are two ideas that we use to achieve this thing that is idealistic, which is most likely to be used in the near future. It's impossible to be sure, but we can get close to it. All right. To replace what won't be needed for the longest time. Again, totally idealistic. How do you know that this chunk might be just about to be called? And you hoof it out, right? Optimum performance cannot be achieved because the OS cannot predict, right? We don't have a crystal ball. But several suboptimal, we call it, replacement strategies exist. We'll come to them. So these are some ones that are out there. Random, just pick one. Okay, unpredictable, never used, total bullshit, right? First in, first out. Choose the page. We just did this one. Choose the page that has been in storage the longest. That's what we did to get rid of the 1 and 2. This will discriminate against pages that are in constant use, like a text editor. Okay, so that's fair enough. It would be a poor choice as the page would need to be recalled to memory almost immediately. All right. So if you're using a text editor, you load up the editing pages first, and then other pages, because you're then text editing, the pages that are in there are where your text is, and the ones that actually do the editing will become older over time, and you'll end up throwing them out as you move on to editing a new page. But then you have to bring up the actual software that does the text editing. You have to bring it back in. Okay, hopefully you can see that. But anyway, it's an algorithm. What we do. Least recently used. Choose the page that has not been used for the longest time. Right, okay, so this page is in DRAM and I haven't used it in a while. So I'll get rid of it. But guess what? Sadly, it might just be about to be used. So that wouldn't be such a good idea. But the main reason why it's not used is there's the overhead involved in implementing it. You would have to maintain a counter or some sort of time thing in your page table to figure out which one to get rid of. And the next one's even worse. Least frequently used. Count the number of times a block has been used, replaced with the one with the smallest count. So this page has been used 20 times in the last X milliseconds. This page has been used 4 times in the last X milliseconds. I'm going to hoof out the one that's only been used 4 times. Again, this page might be the one that is most, if you could hoof out one with a small count that's only recently come in and it may be just about to be used again. So again, none of them are ideal. None of them are optimal, right? But they exist. So remember I said there's 2 ways, just to reiterate. The crystal ball approach is don't throw out a page that is about to be used in the future, right? That's the idea, and it's what's called the optimal algorithm, and we will use that algorithm. Unfortunately, it doesn't. It's idealistic. It doesn't exist. So what we do is we rely on these 2 aspects of locality to come up with the ideal approach, right? So temporal and spatial. What does that mean? Locality. Temporal locality means pages referenced recently are likely to be referenced again in the near future. Right. So if you're doing loops, jumping to subroutines, methods all the time, using certain things off the stack, whatever, using the same variables all the time. Okay. What that means is I have recently been there, so therefore I will keep these ones. They mightn't be in the same, they're not in the same chunk. The chunks mightn't be beside me, my chunk that I'm running in at the moment, but I keep accessing these chunks for some reason, therefore I will keep them in memory, all right? So it's called temporal locality. Spatial locality essentially means that if chunk n is in memory, then do you know what? I'm going to keep chunk n-1 and n+1 also in memory, because the odds are high, the way programs are written, sequential code execution, I will need it again, right? So that's how you can get as close as possible to ideal, right? You can never get to total ideal, but that's how you can get as close as possible to ideal. The most important consequence, blah, 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 is a program can run efficiently, blah, 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 what we do. Okay, the real world. Linux and page faults. Okay, so I think there isn't much here other than you can read them and to get a good example. What's a page fault? An example of a page fault. Okay, it's exactly what I said. All right, fine. Yeah, I'm not going to read that. Okay, you can read it. It's the exact same thing that I've just been talking about. The minor one, okay, I will read this again because I think this one is harder to understand. Okay, special case scenario called a minor page fault, which occurs when code or data needed is actually already in memory. So the example I gave you was a DLL, all right? Example, if a user is running a web browser, then the memory pages with the browser executable code, this is a different example, right? The browser are shared across multiple users since the binary is read only and can't change, right? So in other words, if I have a server and multiple people can log on to that server and they're all browsing, right? The browser executable code will be in your DRAM, but multiple people are browsing at the same time. If the second user starts the same web browser, then Linux won't load all the binary again from disk. It will map the shareable pages from the first user and give the second process access to them. That's essentially what it does. It just updates the page table. In other words, a minor page fault occurs when the page list is updated and the mmu configured without actually needing to access the disk. That is the important point. The difference between a minor and a major is a major will basically definitely incur access to the disk to bring a page in from disk to DRAM, whereas a minor does not do that. It only accesses the page table. It updates the page table. Okay, so hopefully everybody gets that. There's a major, forgive the pun, there's a major difference between a minor and a major. And obviously a minor takes more time. So you are looking to minimize the number of a major takes more time. You're looking to minimize the amount of page faults you have. Major, Jesus, you're looking to minimize the number of major page faults you have. Okay, so I'm going to leave it there for today, all right? Because what we will do, I'll just give you a quick look before we go, right? So that you'll be glad to know that's all the theory crap, right? So let's just have a quick peep at what we're going to do the next day, okay? So let me just set this up. Just so you know. Okay, so what we'll do the next day is just a reminder of what's going on here and some discussion, right, and algorithms, right? So basically we're going to look at 3 algorithms. We're going to look at optimal, which is the one where you look in the future. We're going to look at FIFO, which we already mentioned, and we're going to look at another one called LRU, which we also mentioned, which is least recently used, right? And we're going to compare all of them to each other. And so, for instance, this, just so you get used to the diagram, this is the order by which this process is going to use these chunks. This is what's in DRAM at the moment. We're going to compare FIFO to optimal, okay? So we'll go through these next week, and then the following week, we will go through them in the labs, all right? And they are definitely in some shape or form. And there's loads of questions I give you, loads of practice you will have, but they definitely come up on your CA2. And I'm going to tell you now, these are the gimme marks on CA2. Do not screw these up, right? Because other marks on CA2 can be hard to get. There's semaphore stuff and scripting synchronization stuff. Some of them can be quite difficult. These I consider as gimme marks, all right? So you're mad if you don't knuckle down and make sure you know how to do these, right? Because these are marks you want to get to make your life easier, all right? So that's what we will do next week. We'll do some examples in lecture, and then the following week we will do labs. Any questions on that, ladies and gentlemen? We end up with 58. Not bad for this time of year. Any questions? Yes, no, maybe. Not saying any. Okay, so I'll punch up these 2 videos so you have them, all right? And please make sure that you do this week's lab. And if you, for some reason, some of you did miss this week's lab, I'm not putting this week's lab up on video, right? So you better turn up next week, because next week is your last chance to understand what's going on with semaphores and scripting as regards synchronization. And semaphores and scripting are worth at least, I can't remember, but at least 10 of the 25 marks for your CA2. So my advice would be, if you haven't turned up this week for the lab, make sure you turn up next week. Otherwise you're throwing away all those marks and you are making life difficult for yourself. All right, so if there's no questions, I shall leave it at that, and we will see you next week for labs, where we, as I say, we'll do the final amount of semaphore and we'll do some script synchronization, which is tricky. It goes back to that lock test example we did a month or so ago. All right, okay. Talk to you next week. Be good.